everyone. My name is Harnit Saini. I am an assistant professor in Ajay Kumar Garg Engineering College. Today, the topic of our discussion is virtual memory. Virtual memory, first of all, we should know what is the background of this. Separation of user logical memory from physical memory. What is a logical memory? It is a logical means it's a virtual memory where we keep the pages which are frequently used, which will be used by the program throughout his lifetime, and only part of the program needs to be in memory for execution, right? What part of the program is executed, that should be there in the memory. Logical address space can therefore be larger than the physical address. There may be situations where the program require a large number of pages, right? But the physical memory is smaller than that. Then we can have virtual memory larger than the physical memory. It allows address space to be shared by several processes. If many processes are sharing the same pages or the same memory references, we can allow them to share it. Allows more efficient process creations. Virtual memory can be implemented via demand paging and demand segmentation, right? Now, when virtual memory that is larger than physical memory, what is the scenario? We will discuss this. Suppose this is the virtual memory. We are having these many pages from 0 to n in this, right? And this is our physical memory, which has less number of pages compared to the virtual memory. Now, that means there are some pages which are in this but not in this, right? So that pages have to be stored in the backing store, and whenever we require them, we have to bring it into the physical memory from the backing store, right? And then, first of all, this virtual memory will be mapped to physical memory through the page table or the memory map, right? Then it will be checked that whether the page is there in it. If it is there, then it will be accessed. And if it is not there, then it has to be, backing store has to be referred to that, and the page will be brought into the physical memory. Now, what is demand paging? Okay, bring a page into the memory only when it is needed, right? If there is a requirement of the page by the program, then only bring that page into the memory. Then less input output is needed in there, less memory is needed, faster response, and more users can be accommodated in that. These are the benefits of demand paging. See, let's go to the previous slide. Like here, the pages are limited, right? If we require any page from this which is not present in this one, then only we will bring this in the physical memory. This is the meaning of demand paging, right? Pages, when page is needed, you have to refer to it, right? If it is an invalid reference, that means it is not in the memory also and not in the backing store also, then we have to abort that. But if it is not in the memory, then we have to bring it to the memory with some mechanisms, right? We will discuss these mechanisms in the further presentation. Now see, there are two terms associated with demand paging, that is swap out and swap in, right? When there are some, see, what is the scenario? There are limited pages in the main memory. Now let us suppose all these pages are filled, right? We are not having any empty space in it. Now what you will do, OS will do what? Then it will clear one frame, it will send back to the backing store, and in this place the desired page will be kept, right? When we move a page from the memory to the backing store, then it is called swap out. And when we move a page from backing store to the memory, then it is called a swap in, right? Now see, when there is a page table, we have here the frame numbers and we have some bits associated with it. It is 1 or either it is 0. That means if the this is valid or invalid bit. If it is 1, then it is valid, and if it is 0, then it means it is invalid. Valid means this particular page is present in the memory, right? And if it is 0, this means the page has to be brought from the backing store. It is not in the memory. Now see, with each page table entry, a valid and invalid bit is associated. This one. This is the valid and invalid bit. Right? Initially, the valid invalid bit is set to 0 on all entries. Right? Initially, all are 0 because initially we keep all the pages in the backing store only. Right? Now, this is the example of the snapshot. During address translation, if valid invalid bit in the page table entry is 0, that means it's a page fault. What is the page fault? Page fault means the page desired is not there in the memory and we have to bring it from the backing store. Right? That is the page fault. Now see, when the page table, when pages are not in the main memory. Now let's take an example. See, this is the scenario of a logical memory. These are the pages that will be required by a particular program, right? A, B, C, D, E, F, G, H. These are the requirements. Now, what's the page table says? This is the physical memory. We have F, we have C, and we have A in the memory. That means A, F, and C are in the physical memory. Now, A is kept at 4, means 4, and C is kept at 6, C has 6, F is kept at 9, C has 9. Now, all these 3 bits are valid, means they are set to 1. It's V, valid. That means these pages are present in the physical memory, right? All others are invalid. That means they are not present in the memory or they are empty, right? And you can see here we have A, C, F here also, and B, D, E are only in the backing store. When we bring a page into the physical memory, only a copy of the page goes to the physical memory. Whatever updations are being done here only, and once you save it or you put a commit command, then these changes are being made in this file, right? Now, what is a page fault? If there is ever a reference to a page, first reference will trap to OS, that is called a page fault, right? Now, when a page is required and it is not present in the physical memory, then you have to tell to the OS that we are requiring one page from the memory. That is called a page fault, right? This is a page fault. Then what will OS do after that? OS looks at the another table to decide whether it is an invalid reference or it is a invalid bit or whatever it is. If it is an invalid reference, the OS will abort that particular trap or fault. And if it is just not in the memory, then OS will take the steps to bring it into the memory. Now, what the OS will do? First, he will find the empty frame in the physical memory. Now, that swap the page into that frame from the backing store to the memory, then it will swap that page. That means swap in. Reset the tables. Now the invalid bit will be set to valid bit because now the page has come to the physical memory. Then bit is set to 1, that means valid. Restart the instruction and it will restart it from the least recently used algorithm, which we will discuss in next presentation. Now, how to handle a page fault? You should know all the steps. First, number 1, right? When a page is required, page table is searched in it, right? When it was searching this way, we found that it has an invalid bit. Invalid bit means that page is not present in the physical memory. Something has to be done to access that page. So whatever, now it will go for the help to operating system. It will generate a trap and tell to the operating system that I want this particular page. I want, suppose, X page I want, right? Now operating system says okay, and operating system will search that page in the backend store, because now the function of operating system is started, right? It will go into the backend store and will search the page number X here, right? Now it founded the X here. Now it will bring back to the physical memory. Wherever it is, there is a free frame, then it will put that X in that particular page, right? And then it will update the page table. Now this bit will go to valid bit, because it is, this X is now in the physical memory, right? And then this page will be accessed by the program, right? What happens if there is no free frame? Now, see the previous slide. When X has to be brought from here to here, if there is no free frame, then what has to be done? Then what OS will do? Then page replacement has to be done. Some or the other page has to be selected. It should be moved back to the backing store, and in its place the new page, that is X, has to be brought into the physical memory. Now find some page in the memory but not really in use, swap it out. Now we will select that particular page or that is not being used by the program at that time, right? Then we will send it back to the backend store, and this process is called swap out, right? We will swap it out, and for this selection that which page has to be replaced, there are different algorithms. We will be using one of that algorithms to select the victim, right? Then performance, then want an algorithm which will result in minimum number of page faults. We have to select that algorithm which will result in minimum number of page faults, so that with minimum wastage of time, we are bringing the desired page into the memory and CPU time is properly utilized. Same page may be brought into memory several times. Now there can be scenarios, some pages are brought into the memory, but at that particular moment, 2 or 3 pages are not required. So we can send it back to the backing store, right? And after that time, it is required again, then we can bring it back also. It's not that once the page is brought into the physical memory, the program has to finish the work, then only it will be sent back. No. For at that particular time, if it is required, then only it will be kept there. Otherwise, it can give the chance to some other program and other page, and that particular page can be swept out and the new one can be swept, right? Now, how to check the performance? Now, page fault rate, if it is 0, that means there are no page faults at all. All the pages that are required by the program are there in the physical memory. And if it is 1, that means every page that it is desired is given to the program after a page fault. Means none of the pages required by the program are there in the physical memory, and they have to be brought from the backing store every time, right? See, if P is 0, then there is no page fault. If P is 1, every reference is a fault. Means every time the page is desired, it has to generate a trap and OS will find the page and free the frames and bring the desired page into the memory. This process will go on for every reference to the page that is made. Now, effective access time, if you have to calculate, what's the formula for that? Effective access time means 1 minus P. What is P? P is page fault rate. into memory access time plus the page fault overhead, the time required to create a trap and then bring the page, then page swapping, the time required to swap the page out, then swap in, time required to bring the page into the physical memory, and to restart overhead. All these times are added, then the desired page will be given to the program, right? So this much time is required, that is being done, right? That is being wasted, you can say, for bringing a new page from the backing store to the physical memory. Now see here, let's take an example. Suppose the memory access time is 1 microsecond, right? And 50% of the time the page that is being replaced has been modified and therefore needs to be swapped out. The half of the time is there when the page is being replaced, means it is being replaced from the backing store, swap in, swap out, process is going on. So 50%, whatever the total time is, 50% of the time is done in this only. To swap page time is what? 10 milliseconds, suppose, means 10,000 microseconds, right? Now the effective access time, 1 minus p into 1 plus p into 1500 means 10,000 is the time, is the proper time for the page to be run, and 50% of the time is wasted in page replacement, right? Then the total time is 1500, right? Now, this memory access time is 1. It's here, this one, right? Now, we are saying that there is a page replacement in there. That means 1 minus p is p, 1 and this much in microseconds. This is the effective access time required if you count the number of page faults, or at that time. If you have the value of p, then you can access this. Put the value of p and then you can get the time there. Process creation. Virtual memory allows other benefits during process creation, right? Copy on write and memory mapped files. Copy on write. Copy on write means, if we have discussed earlier also that a copy of backing page that is there in the backing store, only the copy of it is gone into the physical memory. And if there are any changes, when the user or the program presses commit, then only these changes are being done in the backing store, right? So if now here there is an overhead to update that copy also. But according to the virtual memory concept, if you are just seeing the value or reading the value and not updating it, then there is no need to update the page that is stored on the backing store, right? That means you are not to perform this write process again. So this will save the time. Okay. Copy on write allows both parent and child processes to initially share the same pages in the memory. If either process modifies a shared page, only then is the page copied, otherwise not. Okay. COW allows more efficient process creation as only modified pages are copied, not all. Free pages are allocated from a pool of zeroed to out pages, right? And whenever the pages which are free now, which are being used by the program and now they are free, now they can be collected differently. Now, what are memory mapped files? Memory mapped file allows the file input-output to be treated as routine memory access by mapping a disk block to a page in memory, right? A file is initially read using demand paging, right? A file is accessed, which is done by demand paging, means it has to be brought from the backing store to the physical memory. A page size portion of the file is read from the file system into a physical page. Subsequently, read writes to and from the file are treated as ordinary memory accesses, right? Simplifies file access by treating file input output through memory rather than read write system calls. Now, we are not to tell the OS that we are reading or writing the file. That means we are not to generate the calls to OS that we have to perform read or write. We can do it with the simple memory accesses. Also allows several processes to map the same file, allowing the pages in the memory to be shared, right? Now, there are several pages in the memory that are being required by different programs. So, they can be shared. Let's see the diagram for this. See, this is process A and this is process B. Process A requires 1 to 6 pages and process B also requires 1 to 6 pages, right? Now, these are the disk files. This is a backbone store having 1 to 6 pages. Now, each and every page, for example, we check 3, right? This is also accessing it. This is also accessing it. And this has been brought into this by the with this swapping process, right? So, now with this place, we can fulfill the needs of 2 processes at a time by sharing. Thank you very much.